In this particular lecture, I will start a new module, that is distribution systems with distributed generation. Okay. So, at my introductory lecture, I mentioned that distribution networks are slowly upgraded or slowly changed what it is presently, okay, and what it was just 5 years back. Why these changes took place? The reason is the integration of distributed generation system. Okay. So, in this particular module, we will learn what is distributed generation, how to define distributed generation, and what are the challenges involved with the integration of distributed generation or penetration of distributed generation into distribution networks. Okay. So, first let us define what is distributed generation. Let us define what is distributed generation. So, this definition you can get in this paper authored by Ackerman, published in Electric Power System Research Journal, volume 57, page number this in the year of 2001. So, this paper, if you follow, it will give you a nice overview on what is distributed generation and how can we define distributed generation. Okay. So, there are in fact, in this paper if you follow, there are various attributes in which the authors define on this distributed generation. Okay. First of this attribute was purpose of distributed generation. What is the purpose of distributed generation? The purpose of distributed generation is to provide a source of active electric power, which is very precise and one needs to understand. What is the use of distributed generation? It is a source of active power, it provides active power to a network. Okay. Then second attribute was what is the location, what are the locations for distributed generation. Okay. So, the location of distributed generation is defined as the installation and operation of electric power generation units or distributed power generation units connected directly to the distribution network or connected to the network on the customer side of the meter. So, this is very important. In fact, according to this Ackerman, these two are most significant attributes while defining distributed generation. Okay. And in its acronym is very famous, used in several of research papers, which is called DG. Okay, which is called DG. Okay, there are some nomenclatures to specify the same thing, that is distributed generation. I will come to that. Okay. But these two are the important attributes to define distributed generation. One is what is the purpose of distributed generation? Its purpose is to provide active power to a network. And what is the location or what are the locations for distributed generation? So, distributed generations are located directly at the distribution networks or at the customer side of the meters. Okay. And if you follow this particular paper, this is very useful paper, then you will find there are many other attributes, and the authors claim that those attributes are not so significant or relevant while defining the distributed generation. What are those attributes? There are many attributes, like I can write other attributes. First of all, rating, then ownership, third type, Next is environmental impacts. Then next is power delivery. Okay. So, these are the other attributes, and according to this author, they are not relevant. They are not relevant while the defining a distributed generation. Okay. And what do you mean by rating? Many people think that a distributed generation is a smaller version of what conventional generation is. For example, you know that conventional generations or conventional generation units are of 500 megawatt or even higher, or maybe 250 megawatt smaller unit. And some people think that a distributed generation means it will generate a few kilowatt up to 1 megawatt and so. Okay. But according to this definition of Ackermann, he said that the rating is not important. Why it is not important? He argued that suppose there is an industrial customer, okay, and this industrial customer is basically directly connected to sub transmission networks, let us say 132 kV or 110 kV networks, and it is fed from this particular sub transmission network 132 or 110 kV. Now, if that industrial customers integrate a distributed generation source, a large solar photovoltaic panel or a wind park at its premises, and it is connected to the customer site of the meter, then also, and its capacity may be 100 megawatt and so. In that case also, that particular system should be categorized as distributed generation, because this is connected to customer site of the meters, irrespective of the size of the distributed generating units, or irrespective of the voltage levels of the networks, or irrespective of the whether it is a irrespective of the fact that whether it is a transmission network or sub transmission network or distribution network. Okay. So, that is very important. So, the rating does not matter here, ownership also does not matter. In fact, a distributed generation can be owned by a distribution utility, or can be owned by some local independent authority, or whoever, that does not matter, at least in the defining that distributed generation terms, okay, and that is not relevant. Similarly, the types of distributed generation, I will come to that in the next slide. In fact, there are various types of distributed generation units, which may be categorized as conventional types, or non-renewable types, and renewable types. Okay. So, renewable types include solar, photovoltaic, it includes wind turbine and so and so. So, those are not important. So, we cannot categorize, or we cannot define a distributed generation in view of its types, or in view of the technology used. It can be solar, it can be wind, it can be fuel cell, it can be anything. Okay. As long as these two attributes satisfied, we can categorize that, or we can define it as distributed generation system. Now, as I said, there is no point of environmental impacts, or there is no relevance of environmental impacts while defining a distributed generation terminology. In fact, some units are having higher impact or higher emission, and some units may not have any emission at all. So, those things cannot influence or cannot be relevant in defining distribution generation. Similarly, this point of the power delivery is also does not matter. It can the common belief is that distributed generation means that it has to deliver power locally, but actually it does not. It may so happen that a distribution generation unit provides or feeds power to the grid as well, okay, when it has surplus power. So, that point or that attribute that a distributed generation has to deliver power locally does not relevant while defining the distributed generation according to this Ackermann paper, and this is very first paper of this kind. Before this 2001 there were many research papers published, and they are available in the literature, where people use different terms to define this distributed generation. Somebody may call this embedded generation, somebody may call that dispersed generation, somebody called it distributed energy resources, and so and so. But there is no standardized definition before this Ackermann defined this. Ackermann and its co-authors defined in this particular paper what is distributed generation and how to define this distributed generation. Okay. Now, as I said, although types are not significant or relevant while defining the distributed generation, but we have different types of distributed generation units or different types of DG units, which can be categorized as these two group. One is called non-renewable type, which are conventional type of gas turbine units having smaller capacity, but directly integrated to the distribution networks, or maybe renewable type of distributed generation units. Now, again the question is, what do you mean by renewable energy source or renewable type of distributed generation unit? The answer would be those units which run by those sources which are not subjected to depletion are called renewable type of distributed generation unit. For example, wind. How this wind turbine based distributed generation unit works, I will explain in the further lecture, but you might be knowing that as long as the force in wind exists on the earth, it is possible to extract power from that, and that is what exactly wind turbine based distributed generation system is doing. Okay. Now, solar is another renewable type of distributed generation unit, in which this solar irradiation or solar insolation, solar light is basically used to convert energy. Okay. There is another form of solar energy which is concentrating solar energy, in which the heat available in solar irradiation or solar insolation is used, but here the intensity of the solar irradiation is used, that is called photovoltaic. In fact, these are there are two parts in solar, there are two forms of solar based distributed energy source or solar distributed generation unit. One is called photovoltaic unit, another is called concentrating solar plant, that is CSP. I will come to that, I will discuss this. But apart from that, small hydro geothermal biomass, they can be categorized as renewable energy source, because they use the resources which are not expected to deplete. Okay. Now, there is another term which is used often in similar type of literature, that is called distributed energy resources, DER. Okay. Now, what do you mean by DER and what is the difference of DER and distributed energy source, that is what is the difference of DER and DG? So, the basically in many papers you can find DER is often called as DG unit, but DER is basically whatever type of energy resources which are distributed, okay, in nature, which may include DG or may include batteries or storage units as well. Okay. Now, although as I said the types of capacity or rating of types and capacity both are not relevant in defining distributed generation. In fact, distributed generation can be of different types, can be of different ratings, we cannot define, we cannot restrict that that much capacity or that much megawatt should be the upper limit to define distributed generation unit, or that much kilowatt or megawatt should be kept as the lower limit. We cannot simply define distributed generation with upper limit and lower limit, but there exists some categorization, and one of them is provided in that same paper, Ackermann paper, where you can find based upon the capacity DG units are categorized into 4 different groups. One is called micro distributed generation, which is of the capacity of 1 watt to 5 kilowatt. It means that this type, this micro DG can be directly integrated into a domestic customer at their rooftop. Okay. Nowadays, you may find this is a common practice that even domestic customers also integrate rooftop photovoltaic panels, and they are directly connected at the customer side of the meter, okay, and the surplus power is even fed to the grid, okay, and this type is basically called micro DG. And small distributed generation is those which are having capacity of 5 kilowatt to 5 megawatt. See, these are very specific values I am talking about, that 5 kilowatt or 5 megawatt, but actually this is not so precise, but one needs to make some classification or some categorization, and this can be a way to do that. Okay. So, small distributed generation are of 5 kilowatt to 5 megawatt, which can be directly integrated to a typical rural distribution networks even. Okay. And medium distribution networks, medium distributed generations are of the capacity 5 megawatt to 50 megawatt, which can be integrated to even urban or metropolitan distribution networks, which are having higher demand, which are having higher capacities as well. Okay. And large distributed generation, as I was talking about, it is from 50 megawatt to 300 megawatt. According to this definition, which can be, as the example I gave to you, that a typical industrial customer can directly connect, can be directly connected to a higher voltage, because this 50 megawatt and 300 megawatt is very big value, very high value to integrate in a typical 11 kV primary distribution network, it is not feasible. So, one needs to connect this to a typically higher voltage distribution network, which may be 110 kV or 132 kV, which are often we categorized as sub transmission system. Okay. So, if a industrial customer is directly connected to a sub transmission network of having 110 or 132 kV voltage level, one can connect large distributed generation as explained. Now, I will discuss some sort of challenges and some sort of impacts, which are very important of integration of distributed generation into distribution networks, which are very important, and that is why I kept this part in this syllabus. Okay. We have to understand what are the impacts and what are the challenges as well to integrate or with the integration of distributed generation into distribution networks. Okay. Now, before that one can also understand that a DG unit can be defined as standalone unit or grid connected unit, but we are talking about mainly grid connected unit. If it is a standalone unit, then it is directly connected to the customer, we do not bother on that. Then it is the customer responsibility or whoever the owner of that DG, it is their responsibility to properly operate. But grid connected DG will have some bigger impact on distribution networks, those things we will be discussing here. So, a standalone unit always provides some demand and it needs of course storage, so that if there is a imbalance between demand and generation, then part of the energy can be either stored or delivered by the storage unit. But grid connected system does not require any type of storage, and that is why it is more relevant to connect it to the grid, because grid itself infinite system. Okay. So, there is another terminology which is used in this context, that is called point of common coupling, PCC. It is the point or connection point where a DG unit, a distributed generation unit, is connected to the network. For example, if we have a let us say 10 node distribution network, and at node number 7 a DG unit is connected. So, the point of common coupling for that DG unit is node number 7. Okay. This is a typical illustration of distribution network with DG units. In fact, this part is basically distribution networks. So, this is our distribution networks. This part is sub transmission network as it is mentioned, and this part is transmission system, and this part is generation system. So, this figure is giving you an idea that where we can connect a typical distributed generation unit or some typical distributed generation units or DG units in short. Okay. So, this is generation or generator. So, we have conventional generators which are of synchronous generators mostly, which are used in conventional power plant in India, and then we have typical transmission systems. We have then next level, that is sub transmission system, and finally, we have distribution network. So, in this distribution network you can see we have these are the feeders, these are the feeders. These are the distribution feeders. Here 4 number of feeders are shown, and one typical feeder is shown over here, which is having a single phase lateral here. This is our distribution transformer. And these are the loads. And one typical load is shown is as home, where we can connect photovoltaic system or solar photovoltaic system, which is one of the DG unit in that network. So, we have a number of loads there. It may so happen that each of the house may have the similar kind of photovoltaic system as distributed generations unit. Okay. But apart from that, we may also have storage which is located in the substation itself. So, this is located in the substation itself. So, this is a kind of storage, and we also have large amount or large rated distributed generation system directly connected to the sub transmission system. So, here you can see a solar or wind, a large photovoltaic system which consists of multiple numbers of photovoltaic panels and aggregated capacity may be in the level of 100 megawatt, and so can be directly connected to the sub transmission system. Similarly, not even 1 megawatt, it can be 100 megawatt as well. Even if we have a large wind park, offshore wind park, and this can be directly connected to the sub-transmission system. So, you can identify that in a typical power network, where are the potential locations to integrate DG. It can be located in sub-transmission network, or it can be located directly in the distribution networks, and it can be connected in a distribution network directly, or it can be connected to the customer side of the meters. Okay. Now, we will go to the techno-economic and environmental benefits of DG integration, okay, because DG integration will have some challenges and some benefits. Okay. So, one of the benefits is of course, the reduction of pollution, particularly with the use of renewable energy sources. Okay. So, as you know that global warming concerns with the use of non-conventional or non-conventional energy sources, particular like thermal power plant, and this can be somewhat mitigated if we have a good number of DG units. Okay. Also, this, as I said, the fast depletion of fossil fuel reserves is one of the concerns. Okay. And since this renewable type of DG units, they run with the resources which are not to be depleted and which are not to be at all concerns of this operators or owners of these generating units. So, we can use them. And also DER are usually modular units. It has lower energy density, and it has smaller capacity, and it depends upon the geographical condition. Okay, as I said, so this is not benefit, this is one of the challenges. And also this power quality and reliability improve. How it is improved, I will come to that, and if energy efficiency also improved with the integration of DG. I will come to that. Now, with the integration of DG, with the integration of distributed generation, our distribution networks are slowly in the process of transition, to a active distribution networks from the usual passive distribution networks. So, till now in most of the part of our country, distribution networks are of passive. So, there is no active source anywhere, and it is directly connected to the grid with a substation, and we consider in our analysis so far that substation is our feeding point, and there is no other feeding point, and that is why since our distribution networks are of radial. So, power flow is unidirectional, starting from the substation towards the customers or towards the loads. Okay. So, for passive distribution networks, there are no DERs, and DER capacity integration to the existing network is also limited. Okay. But active distribution networks are of well equipped, and they are particularly designed to integrate higher amount of DG, higher amount of distributed generation. Okay. So, they have distributed management system for control and planning of their operation of the network with these distributed generation units, and they have the provision of ancillary service. They have the possibility of islanding operation of the whole system. It means that if you have sufficient amount of generation which can supply all the customers load even at the peak condition, even during the peak time, then we can go for islanding operation whenever there is a disturbance in the grid, or whenever there is a blackout in the grid. So, this active distribution networks, there are some issues. So, we have to understand several benefits, technical and economic benefits for enhancing security, for reduction of investment cost, because why it is so? Because due to this presence of the distributed generation, we may defer some of the infrastructural changes which are inevitable in a typical distribution network. For example, if you have a distribution network which is located where there is a continuous growth or very steep growth of the load, then of course, to cater or to accommodate this higher amount of demand within next few years, these distribution networks need to have infrastructural change, and that is called reinforcement of equipment. Now, this can be deferred if we have a local DG, which will cause somewhat reduction of power flow of a particular feeder. How it is happening? I will come to that with my simulation results. And also, due to this particularly renewable type of DG units integration, the operating cost would be somewhat reduced. So, these are the economical and technical benefits, but we need to have new control techniques, because this is very important that conventional type of passive distribution networks, as I said various times, it operate with the idea of or with the property of unidirectional flow of power, and that is why its protection system is designed considering the fact that this unidirectional flow of power. Okay. But due to this integration of DG unit, no longer this unidirectional flow of power will exist, and therefore, this protection system needs to be redesigned, completely redesigned. Okay. And also the control new control technique is to be there. Another important issue is that this in distribution network there is very typical distribution networks, there are small number of sensors connected, so that we can have an advanced level of control and monitoring of a particular equipment. Not many distribution networks are fully connected with supervisory control and data acquisition systems, SCADA system. So, therefore, it is very difficult to get a centralized control of whole system, okay? And that is one of the challenges, particularly in active distribution networks which are having DG unit. Okay. So, we need some changes, in order to have this smooth transition from passive to active distribution networks. Now, what are the changes we require? As I said, protection system should be completely redesigned, and accordingly new control strategies to be devised. Okay. So, many sensors and measurements should be required, so that the whole network state would be fully visible, and also network management, communication system and data acquisition and data extraction system, those things are inevitable in order to have a smooth operation for this active, so called active distribution networks. Now, there is a definition, that is renewable energy penetration, and this definition is basically this average penetration. This average penetration of renewable or any type of distributed generation unit is defined as that annual energy, it is the ratio of annual energy generated by those generating units or those generating stations to the total annual energy delivered to the load, or it is basically the fraction of energy which is being supplied by the DG units, okay, in a particular year. Okay, that is called average penetration. You can get it from Gonen book, and instantaneous penetration is basically that it is a time varying quantity. So, it is ratio of power generated by a renewable generating unit to the total power delivered to the load. Okay. So, typically instantaneous penetration is used to be much higher in a particular instant of time, and it is variable throughout the day. So, instantaneous penetration is variable throughout the day, throughout the minutes even, and its maximum value is somewhat higher than the average penetration. Now, we can also define different DG units on the basis of their operation or their ability to provide reactive power. So, one type of DG unit, in fact, as I should say at this point that the conventional power stations in India or even in other countries, in the conventional generation comes from the fossil fuel based power plant, where we have synchronous generator, Now, the changes that main change that you can see in this distributed generation system is that no longer we use synchronous generator. Okay. No longer we use synchronous generator, we use different types of generators, and we also use converters to generate this power or to feed this power to the network at the point of common coupling. Okay. And therefore, we can categorize these DG units out of three different categories. In one category is of course, we can keep it similar to a synchronous generator, which can deliver active and reactive power. But there are some DG units which can only operate at unity power factor, thereby it can supply only active power, it cannot supply reactive power. And there are some DG unit which will supply active power, but it will consume reactive power, particularly if you have a induction generator type of generating system. Okay. And we can categorize like them, and there are some DG which can be operated as voltage control mode, that is with a fixed magnitude of voltage, which is basically rare. The controlling voltage at the DG level is very much rare, and it is subjected to the regulators or subjected to the regulation. Okay. So, DG integration capabilities is a type of plug and play. It support active and it can support reactive power as well. It can improve power quality, it can have fault right through capability. Now, I have some simulation result for this DG integration. First, let me tell you how I have done this simulation for this DG integration in order to understand the impact of DG integration into distribution networks. Okay. So, this slide will give you how I have done this simulation. In fact, whatever I will be showing, I will show you three different systems, and out of which 2 works are of our personal works. Okay. First of all, how do we simulate the DG integration into distribution networks? These are the steps. Okay. Firstly, you should identify the location or node where I should put a DG unit. Okay. Then you should find out what is the generation of the DG, whether it is providing both active and reactive power, or it is providing only active power. Okay. So, if they are providing both active and reactive power, then how much active and reactive power it is providing. Then third step is to find out if the DG unit provides both active and reactive power, then it is considered to be a negative load, assuming that it does not have this constant voltage or regulated voltage capability. Okay. So, it is considered to be a negative load, and the point where you are basically connecting this particular DG unit, this point might have some load demand as well. So, what you can do, you just subtract this generation from this load demand, assuming that this DG is a kind of negative load. So, here we can assume that DG unit is acting as negative load. So, whatever power demand you have this particular location, you subtract this DG active power in all these three cases, but in one case if DG is supplying reactive power as well, you can subtract this reactive power from this reactive power demand as well, but if it is operating at leading power factor condition or it needs reactive power to operate it. So, you just add this as a additional reactive power demand, and if it is operating at voltage control mode, which are very much rare, in fact I should say, then you can consider this voltage magnitude of the bus as well. So, I did not consider this exercise, I considered basically this assuming that a typical DG unit can provide both the active power and reactive power. Okay. And we have simulated this by 33 node distribution network, as this network is known to you. So, what we did actually, starting from this bus number 2 to bus number 33, I exercise by connecting one DG unit at a time. For example, at one instant of time I connect a DG unit at this bus number 2 or node number 2. Okay. And so, suppose this power demand at this node 2 is P 2, okay, and Q 2, that is reactive power. So, this is active power demand, this is active power demand, and this is reactive power demand. Okay. And at a particular instant of time, this particular generators is providing this Pg amount of active power, and it is also providing Qg amount of reactive power. So, at any instant the DG unit connected to node 2 is supplying Pg and Qg. This is active power, this is reactive power. Okay. And we consider this as a negative load. So, what we will do in the simulation? We will modify this demand, because at this node 2 we have some active and reactive power demand, you have seen. So, we what we will do? We consider this active and reactive power supply of this generator as negative load. What we will do? We will modify the net demand of this active and reactive power at bus 2 or node 2. So, what we will do? With DG integration, we need to modify the active and reactive power demand at node 2 as P 2 dash, P 2 dash is the new demand, is equal to P 2 minus P g, and Q 2 dash is equal to Q 2 minus Q g. So, here you can look this P g and this is Q g. You can see this P g and Q g, they are considered as negative load, and thereby whatever generation they are providing, this generation is subtracted with this demand. So, it may so happen this both P 2 dash and Q 2 dash can be 0, can be positive, can be negative. So, if P 2 is higher than P g, that means the net demand of that particular bus or node, that is at node 2 is higher than this generation at that instant, then net demand would be positive. But if it so happen that if this generation P g is higher than this demand, that P 2, then this P 2 dash would be negative. Okay. Similarly, this if this same thing is applicable for Q 2 dash as well, and so it may so happen that P 2 dash and Q 2 dash can be both positive or both negative, or one is positive, one another is negative, or both can be 0 if whatever generation is basically providing by the generator is owned by the it is basically consumed at that particular location loads only, then it should be 0 and whatever. So, considering this situation and considering this possible location of this DG in different nodes one at a time, I will consider one generator at a time, but at every location we have done the next simulation. So, in order to understand this DG integration or in order to understand the effect or impact of DG integration on these different operational features of power distribution networks, what we did? We first determine these power losses with respect to this, with respect to different size of the DG. Okay. So, what we will consider here? We consider this PG and QG is gradually varying from PG and QG are gradually varying from some PG mean and QG mean to PG max and QG max. And this variation we consider as smooth or continuous variation. We are continuously varying this generation both active and reactive power of that particular DG unit, starting from a minimum value to a maximum value. And this is the minimum value, this is PG mean. PG mean can be 0 as well, and this is PG max. So, PG max is here considered to be 8 megawatt. Okay. So, what we did by varying this PG, that is active power which that DG unit will supply from a minimum value to a maximum value, we have done this forward backward, we have performed this forward backward sweep load flow, and we computed this network loss. It is not loss of an individual line, it is a overall network loss. And if you can remember this 33 node system without DG, the power loss was around 202 kilowatt, okay, around 202 kilowatt. So, what we will do? We will integrate this PG and slowly varying PG from a minimum to maximum value, and for every variation we will compute this power loss and we will plot that. And this same exercise we will be doing for all the buses by connecting one DG at a time. So, what we will see in this particular figure, you can see that for example, this is suppose I do not know, I am just arbitrarily considering, this is suppose the plot of this power loss versus DG power at node 6, let us say. So, what you can see with this increase in this DG power, you can see this power loss is initially getting reduced, and there exists a point where we have this minimum power loss, and then again it starts increasing. Okay. And you can see we have not done beyond this 4 megawatt, or we consider here PG max is equal to 4 megawatt, because beyond that power loss is significantly increased. So, same thing you can see for the other node. So, this is node X, this is node Y, or this is node Z, whatever node you have. So, there are 33 characteristics, and each of the characteristics are of similar pattern, that if we connect a DG in a particular location, its network power loss is initially getting reduced, and there exists a point where you get the minimal power loss, and beyond that power loss starts increasing. Okay. Beyond that power loss start increasing. So, we consider this resulting power loss on which is total network power loss with this DG integration at each and every location for this distribution network, and the pattern is same. So, there are some buses where you can see these power losses, and we did not do it beyond this point, and there are some other buses we in fact, all the buses we consider this Pg max differently, okay, and that is why they are terminated in different points. Okay. And in fact, there exists some of the locations where you will get the minimum value of power loss. It is as low as near to this, it is let us say 65 kilowatt, and this corresponds to the optimum value of DG power, which is near to the 3 megawatt. Okay. So, there is some location, or there are some locations where you get this minimal value of power losses, and of course, out of which one should be the best, and the best one can be considered as the best location for DG integration in order to minimize the power loss. So, here our criteria is to minimize the power loss. Okay. And there is a concept that based upon the same analysis, there is a concept called hosting capacity. Okay. So, in hosting capacity, it is the capacity, it is the because suppose I am a distribution network owner or I am a operator, then the question should be how much DG, how much distributed generation I can accommodate or I should accommodate. This is the important question for all this distribution network operator or distribution network owner. Now, in order to answer that, there is a concept called hosting capacity. In hosting capacity, there is a plot in one axis, this is this axis, this is performance index, and this axis is DG capacity. And suppose we consider that lower performance index is better. So, low performance index, or lowest performance index is the best, as we have in network power loss. So, in network power loss, the lowest power loss is the best solution for us, because we are in fact trying to minimize the power loss. So, here also the lowest performance index suppose is the best. So, what you can do? You can similar to this these characteristics, you can see this performance index, for example, it is reducing or it is decreasing with the increase of DG capacity, and there will exist a point where we will be having lowest performance index, which is the best value, and corresponding to that we have the DG capacity here, and this DG capacity you can consider as the optimum DG capacity. So, according to this hosting capacity concept, that it is the capacity of DG which can be integrated into a distribution network without deteriorating the performance of the network. Okay. So, if you consider that I will consider this DG capacity corresponding to the best performance index, one of that is best power loss, then this is the optimum point for DG integration or optimum capacity for DG integration. Okay. But if you consider that this much of in order to maximize this DG capacity or in order to increase the DG capacity, this much of deterioration in performance index is acceptable. So, here you can write as, so suppose this is the point corresponding to acceptable deterioration. So, you can accept that much of deterioration. So, this is not corresponding to the best capacity in view of the performance index, but if you can accept that much of deterioration, then this could be your hosting capacity. Okay. So, this concept of hosting capacity is another new concept, where this concept you can get in various works, okay, and people are using to maximize this hosting capacity or maximum utilize for the maximum utilization of DG. Now, as I said in various nodes I get different types of minimum power loss. So, for example, at this node 6 I get this is corresponding to minimum power loss. This is for node x, or that can be x, can be any value. So, this is the minimum power loss. Similarly, corresponding to this this particular node, this is the minimum power loss. So, different location we get different minimum power loss, and these minimum power losses are plotted, minimum power loss with respect to different locations of different nodes. So, you can see there are some locations you get minimum power loss as same as the actual power loss without DG integration. So, this location minimum power loss is same as that of power loss of the network without DG integration. It is close to 200 kilowatt. Okay. So, thereby you can understand that these locations, that is starting from node number 19 to node number 22, 23. So, these are the locations where DG integration will not be beneficial in view of the performance index, that is power loss. So, if you integrate DG in these locations, it will not be beneficial in view of power loss minimization. But there are some locations, for example, these locations and these locations, where you can get the power loss as low as near to 70 or 65 kilowatt, which is significantly lower as compared to the original power loss, that is 202 kilowatt. So, these are the locations, these are the locations. So, the best, these are the better location for DG integration in view of power loss minimization. Okay. So, one concluding point is that if you consider power loss as a performance index, and if you consider that, of course, DG integration will definitely improve power loss for some location, and there are some location where you will not get any improvement for DG integration in view of the power loss minimization. Also, these are the ratings, or these are the capacity of the DG are corresponding to the minimum power loss point. So, this are the DG in view of power loss, minimization, and you can see even near to the substation, the DG capacity is higher, and if you go to these nodes distant away, the DG capacity corresponding to the minimum power loss. That means, this is the minimum power loss, that is this point, and this is the DG capacity, that is basically this point. Okay. So, every minimum value of power loss corresponds to a minimum power loss as well as a DG capacity corresponding to the minimum power loss. So, minimum power losses for DG integration is plotted over in these characteristics, and minimum or DG capacity corresponding to the minimum power loss is plotted over these characteristics. Similarly, we can also check the effect of DG integration on node voltage. Okay. You can see here we consider minimum node voltage as the performance index. So, here our performance index is minimum node voltage. Okay. So, this is the performance index, and you can see there are some location as well, same locations where minimum node voltage was similar as that of the case without DG integration. Okay. But there are some point here and here you will get. So, you will get best location or better locations for DG integration in view of minimum node voltage. Okay. But here you cannot get any benefit in view of this performance index, that minimum node voltage. So, their minimum node, even if you integrate DG, minimum node voltage would be similar to the network without DG. Now, we have another system, that is IEEE 34 bus system, which is I took from this paper. So, this is a typical IEEE 34 bus radial feeder, and this author said that again if you go for DG integration for 10% penetration, this power loss is improved to this is without DG, this is without DG. So, without DG power loss was 270 kilowatt, with 10% DG at this bus 890 power loss is improved to 190, with 20% DG penetration power loss is further improved to 140. So, this is at bus number 890. So, this is probably bus different buses, even this 10% and 20% penetration, this shows that power loss improved. Now, we have another network, that is SICRE residential network. This is also work of power group. So, what you can see in this particular network, this is the feeding point, and this is also a radial network, and there are some radial loads which are shown over here, RL 2, RL 3, RL 5, RL 4 and RL 1. Okay. And these are the transmit point, where we do not have any load demand, but they are connecting point. Okay. And individual length of this line section, and also this resistance and reactances are given. In previous case studies, what we did, we considered this load demands are of fixed or the peak load demand, and accordingly we studied this DG location and all. Now, what we do here, we consider load is varying and we consider a typical load curve, and also we consider a PV type of, that is photovoltaic type of DG unit, where the generation is also varying throughout the day, because this renewable generation systems or renewable generation units, they are having intermittency and variability. I will discuss this later on. So, that means their generation is very variable throughout the day, and it is uncertain. So, here we consider this is this characteristics is basically the characteristics which shows this PV power generation, and here we have two load curves, one is during summer, another is during winter, and we consider these loads are varying according to these load curves. Okay. So, here our objective is to find this voltage profile throughout the day, okay, not any particular instant of time, which we did in the previous example. So, what we can see here with this 50% penetration level, these are the voltage profiles, individual voltage profiles, these are the time, and these are the voltage profile in per unit, and these are the voltage profiles in different loading points RL 1, RL 2, RL 3. So, with 50% penetration level, you can see although here minimum bus voltage is not specified, but you can see with this location of different locations of DG, one is RL 1, another is RL 2, another is RL 3, another is RL 4 and RL 5, the network voltage profile is improved. Okay. And similarly, with 100% penetration, you can it is further improved. Okay. And this is profile in summer, and same thing is observable even in winter, where usually voltage profile used to be better with reduced amount load demand, and with the integration of DG in both 50% and 100% penetration level, these bus voltages are further improved, but with 100% penetration level, some of the time in some of the feeders experience over voltage. This is another issue that excessive DG integration, that 100% penetration of DG integration may cause over voltage. I will discuss this also later on. So, with this I will stop today. I will continue or I will extend this part on the next lecture onwards. Thank you.